Hello. So I'm Jérémie Chassaing. I'm writing the blog Think Before Coding. And the presentation you will see today is based on a blog post. So if you want more information, you can read it afterwards. And you can find me on Twitter at thinkbeforecoding with a 4. And I've been practicing domain driven design for almost 10 years now at Availpro fast booking, a company that works for hotels for their internet distribution. And what you will see is based on my experience there, on one of my understanding of one part of domain-driven design. And today, the topic will be aggregates. Aggregates is often used and seldom totally understood concept. And I won't explain you aggregate. I want to give you a different vision of that. So let's start with the definition. It's a bit long. So an aggregate, this is the recommendation in Domain-Driven Design, the book, to cluster the entities and value objects into aggregates and define boundaries around each. And you can read the rest. The thing is that here you can see a pattern which is about structuring information. And this is a structural pattern that most people know. But this is not the part I'm interested in. What is interesting is this, which comes just after, and that say use the same aggregate boundaries to govern transaction and distribution. Because aggregates is also on, firstly, a distribution and partitionability pattern. This is what we will talk about. Within an aggregate boundary, applies consistency rules synchronously across boundaries, handle updates asynchronously, keep an aggregate together on one server, allow different aggregates to be distributed among nodes. Great. What does it mean? An aggregate is all about its boundary. And when you have a boundary, we usually talk about what's inside. But since it's a boundary with the outside. And this is what is interesting. When we look at this boundary, what is inside has to be consistent, which means that what is outside doesn't have to. And this is where we get all the benefit from this pattern. So once we have this, we start to have a new grasp on the concept. Question is that people usually don't love some part of this thing when we say you should not have a transaction spanning multiple aggregates. I'm sure you already balanced this restriction, like, yeah, but it's easier to write my code if I can write a transaction around several aggregates. Who has this decision to make at some point? Yeah, we all did, sure. And this is something that we find a question that arises often, but the thing is that usually it shows two things. Either that your boundaries are not right, and maybe the scope of your aggregate should be a bit bigger, or the other thing is often that the boundary could be fine, but there is a hidden process that actually could be splitted in small parts, which would be independent of the other, and that you could do by smaller parts. And actually, what we can see is that the notion of aggregate is here to help you take decisions in a simpler way by creating a locality a locality concern. The thing is that when you want to take a decision, you need some information. And when you need information, you need it locally in your process at some point to be able to process it, okay? But what is local? You can load the data, process it, and then update, save, or do the side effects, and done. But the thing is that when we say we need the information here, the question is, what is here? So I think you know this kind of data. This data is about 1 year old or something like that, and it makes a comparison between real-time actual latency of each of these things and their scale latency so that it helps see the scale, because when we talk about nanoseconds and microseconds, it's hard to feel how slow it is. And this one is just scaled so that one processor cycle is scaled to 1 second, and then everything is scaled. So 1 second, level 3 cache, it's 7 seconds, it's still fast. But once you start to see something like main memory access 4 minutes, oh, it's already a bit far, okay. So main memory is farther than level 1 cache access. And once you start to be on disk, it's 1.5 to 4 days. For most processes, it's okay. But it starts to be bigger. And when you start to make an internet call, 5 years, 11 years. Oh, that's long. That's very far. So one of the usual thing with distributed computing and all that is first law, don't. Okay, don't distribute. Put everything on the same box, everything in memory, everything local, and everything will be fine. There is a lot of people today talking about well-structured monoliths, which are easier to manage and to evolve than complex distributed systems like distributed monoliths, for instance. You know the distributed monolith anti-pattern. So if you can, put everything on one box. But at some point, maybe it will not, one box will not be enough, and at that point you will have to distribute anyway. And once you will start to distribute, this kind of thing happen. You know that? This is just a Chandelier snapshot protocol. This is kind of things you have with any things like Lamport clocks and all that. Doing distribution is hard because ensuring causality effects and all that, you can have a lot of small edge cases like this is slower, this is faster, and all that. And once you start to see this kind of schema, you are not very far from this kind of schema. You know this schema? You know what it is? It's space-time in relativity with particles and all that, with the light cones. No light cones. Line cones are used in the relativity to talk about how far light can have traveled from one point in time and what information can have been propagated at that time. Okay, so everything that is inside the cone can be causally related to an event that happened, and everything that is outside has no way to have any information about what happened at the point where the cone starts. Just because information cannot travel faster than light, so no information can have traveled to this point from what happened at the original point in the middle. Okay. So what we have when we start to distribute is that depending on the speed, the effect will not be the same. If you can take, if you have to make some transaction once a day, even if it takes 5 minutes to go to another system, get the information and process it, it's not a problem. But once you will have to decide faster, like every second, every 10 times per second, 1,000 times per second, you cannot incur a delay of 5 seconds to fetch some data. So you will have to get it back, okay? To collocate it. And collocate it not only in space, but also in time. You have to get the information at the right place at the right time, okay? So the problem is that once you start to go fast, and the propagation of information cannot be considered instant in front of your decision speed, compared to your decision speed, the space doesn't look flat anymore. You have some variance and all that. It's a bit difficult to get it this way, so we will go back. People have been doing this for not years, but for centuries and for millennia. So let's go back about the history of deciding near the ping limit, okay? Deciding near the ping limit, how slow was the ping here? This drawing is a sculpture about the first Roman Empire postal system, okay? So it's about something like the 3rd or 4th century. And at that time, the ping between Rome and, let's say, Lutetia was something like 3, 4, 5 weeks. That's a very long ping. And you couldn't do nothing about that because there was no other technology faster than having some decent roads and having some horses and carriage. So how did we manage at that time? Most decisions were taken on a monthly scale for long distance thing. And to cope with that, what you do is that you can install some more local power that can take local decisions there. So if something has to be decided at a higher level in Rome, you will have a 4 weeks or one month and a half ping delay. But if things can be decided locally with the information you have here, you can decide no, maybe in a few days or hours or something like that. This is a map of the postal system for what I showed you before. So you have some roads from Roma to Milano and to Londonum and Londinium and all that. So it was spread all over Europe. And at the time, this is the best thing you could achieve for fast communication. And still people manage to live and take decisions, right? So let's get some inspiration from that, okay? But with technology, things improved a bit. So this one is 1867. This is in France, the first use of steam engine for the postal system. So it was a bit faster, less horses, but still the same kind of ping, around days and weeks. To travel from one side of France to the other, it's still a bit long with a steam engine like that. So signal propagation is still a bit slow. We get better at this because as people start to improve their capacity to take decisions. They want to take even faster decisions, and so they try to have better communication system to deal with that. So this is a sharp telegraph, and with that there was something like 5,000 kilometers of communication a relay like that to transmit message over France. So you move the arms of the telegraph, and someone is doing the same movement, and at the end someone takes notes of what was the message. And this way you could pass a message from one side of France to the other in a few hours. Yeah, it requires a lot of equipment, people being ready all the time, because if you start the transmission and there is nobody on the other side, it will be longer, all of that. And when you want to transmit a message, you have to go to the special place where you have this device. You cannot just create communication from any point to any point, so it creates more delay and all that, because if you're not near telegraph, you will have a telegraph tower, you will have to move probably by horse or something to the telegraph tower and give your message. It has been in usage for something like 100 years or something. This one is the Morse telegraph. And with that, we started to have something more efficient, because it started to be electric. And the US used it extensively for communication from one point to the others. And with that, you start to have a ping that is under a few hours. I say hours, the message is actually propagated faster, but you still have to take into account that you don't have this device at home, so you have to move to a post office where they have the device, and then when they have time, they can take the message. But this way you could do long-distance communication pretty quickly, and people started to make more transactions every day, because you could have a bank and pass some information from one side of the US to the other. Before that, taking train or things like that were really long. So there was mostly no business or communication from one side to the other. You had less frequent exchange. So we see that with this kind of device, what is near and what is far is changing. Because before that, a country was something that you could not communicate with easily, and then, yeah, country is becoming smaller. This one is the first long-distance phone call by Bell in 1876. And from here, we start to have point-to-point communication between distant parties with something which is like instant feedback. Whoa, that's a great change in the way communication is organized, because now you can call someone on the other side of the country, have an answer now, and you can continue. But the thing is that with that, it's still, we can say it's instant, but for it to be instant, you have to have the other person you want to communicate with available at the time. If it's not available, you have to wait, retry, which can take, as you know, days, the hours or days, but mostly communication delay were even shorter. And you know that? That is ARPANET. Yes, the beginning of internet. Yes, internet like that, you know. Who knows internet here? Yeah, great. Yeah, it's good stuff to know. Internet changed a bit more that because this way we could have a more automatic communication like computers talking to computers without going through humans, and with routing and all that, even when the path is cut, the information can find some other direction. And from here, we started to have things like milliseconds delay between both sides of the world. So yeah, it started in '69 with 4 nodes. In 1993, it was already big. And what we know about the internet now was starting in 1993 with the first web browsers and the beginning of the web. And yeah, today it's everywhere and all the time, and you're working mostly with that. So it's very important. But still, even with that, things are still not instant. From Paris, a ping from Paris to Amsterdam is something like 15 milliseconds, which is decently short. But a ping from Amsterdam to Sydney is 350 milliseconds, which is actually still long. So depending on your process, it's a third of a second from Amsterdam to Sydney, but if you have to take 2,000 transactions per second, you cannot think that something in Sydney is near. It's not possible, okay? And as we start to improve the speed of communication, the distance shrink, but there are still things that are far, like Mars. Mars is far. Okay, whatever you do, Mars is far. Mars is far because, yeah, the thing is that Mars is far because the shortest ping we can have with Mars due to the speed of light is 3.5 minutes. But it happens only a part of the year. It can be up to something like 20 minutes in the worst case, which is long. Now try to operate interactively a rover on Mars with even a 3-minute delay. You move the joystick. I won't wait 3 minutes for that, but you get the idea, okay? And then this thing happens there, but you don't see it now, because you will see the results 3 minutes after. So it's 6 minutes between sending the information, the thing happening, and having the feedback. And you cannot work without feedback on something like that. So how do people work with this thing? The thing is that it's totally equipped to be mostly autonomous. When you ask it to go somewhere, it will go there slowly, and it will watch if there are some rocks or anything like that, and you just tell it, go there, and then it will go slowly, feeding information back as it's moving, going slow, but taking local decision about the state of the land around it, so that it doesn't just fall into a hole or get blocked by a rock or something like that. So it needs some local information to be autonomous. You cannot just think that Earth is near and that everything will happen on Earth. So it makes the design of the rover more complicated. And yeah, so the business already used this before the internet exists. So when you look at the patterns, there was some very interesting thing in a series presentation before about sometimes some of these patterns don't have to be reproduced once you have computers, and this is a good advice. But still, there were a lot of heuristics that have been created by the different businesses to cope with the fact that sometimes some things are far and you need to take decisions faster. And so you have to see how information is organized in space and time to be able to go faster. The problem we have in today for most business which reach some scalability problem is that when a computer started in the 50s, they were a bit slow, but they were way faster than the usual business ping, which was about a few hours because of funds, okay? So you had business organized about a ping which was fun, which was during a few hours or a few business days. And when we put a computer into the mix, everything was instant. So you have computers that can instantly do all the business from everybody except the communication things. So yeah, computers are very fast. Cool. But using computers gives you an edge on your competitors, but the competitors start to also use computers, so they start to be a bit faster, and so you need to go faster on all that, and you get an arm race, okay? But still, all this was limited by speed of phone for long communication. So mostly for computers, the information space-time look like flat. Everything is instant when you need, because everything you need is around, and if it's not, yeah, it's because business, we have to call people and all that. But with the internet and the web, especially in the late 90s and the 2000s, it changed. Because from here, you started to have fast ping, so with this short ping, and still the same business ping, which is around human interacting. Yeah, the ping is just instant compared to a phone call. Yeah, but as people start to reorganize the business to be more internet-centric, it can go faster because less phone call, direct machine-to-machine connection. You remove all that. So at some point you start to go so fast that the ping is the limit, the new limit. So I don't know, who among you think that a ping of 50 milliseconds is something detrimental to your system? I mean, something that is 50 milliseconds is far for your business. I don't know. Tell me, yeah, there are some people, but most of you don't have this problem, no. Okay? Most of you don't have this problem, no. So you will say, again, do I need it? Why should I care? The aggregate model is, you can still use the aggregate model for the organizational pattern it is, because it helps you see how to fit your information and have clearer code and all that. And this is a very good property of the aggregate pattern, by the way. But the thing is that once you start to model around aggregates, is that actually you will be aligned with the possibility to scale. Know why? Because when you have a bad model, or no model, it will never make things more easy, okay? If you have something where you need all the information, everything, and for each decision you need information from a lot of different places to take one decision, at some point scaling will be hard because you will need more and more communication, and you will be anyway limited by the ping. You cannot have ping that is 0. The relativity limit of light propagation just say it's not possible, so you will, at some speed, reach the limit, whatever. Today you don't have this problem, but I won't say that writing distributed systems is easy. I won't lie to you, it's not, okay? It's never easy to write a distributed system, never. But the thing is that having a model that is fit with taking decision locally will make it easier, at least not more complicated than needed, okay? So you will still have to manage things like replication and things like ordering, I don't know, there is sharding and all that, a lot of difficult stuff. But having a model in your domain that is fit for that, you would just have to handle the accidental complexity of the distribution problem, but with a problem that is simple to actually distribute, okay? So start now, start to see the aggregates, find them in the model, organize your information around this notion of locality so that you don't need to go too far. And your system will be easier to scale. And as Cyril was also saying before in his presentation, once your system starts to get rid of all the old limits like phone calls and all that was limiting the speed, your system will start to be fit for going faster. And if you need it, yeah, using aggregates, boundaries, and information, spatial and temporal locality, it will be easier to go to this kind of model. So I know it's a short talk. It's mostly over. You can ask me some question. It was short because it's actually quite simple, but I want it mostly you to have this vision of the space-time of information as being not flat, okay?
Big thanks to Jeremy. We do have some time for questions. Have we got any hands up? Here we go, one at the front. Thank you.
Hi. In your introduction, you mentioned you were doing some booking system or something.
Yes.
I would be interested to hear some interesting story maybe from your own experience where you felt the impact and then the resolution of these kind of topics.
Yeah. For instance, in the hotel business, most distribution systems have a replication of all the hotel data, like prices and availabilities locally. Okay, so you send to this website all the information, and to the other website all the information. Actually, they are competitors, so they don't want to share things. But then they can sell rooms independently, and they just don't communicate together. So our system is doing the synchronization between the systems. But we do it totally asynchronously so that there is less friction. Okay? Some systems we have interacted with didn't like it, and they decided to make some kind of locking mechanism so that if you start to book a room, you lock the room during the whole process. So they ask you, is there still some rooms? And they want you to lock it so that it will not be sold somewhere else and all that. And we had quickly a very big problem with that because they could not sell the room if we were not able to answer in a short time. So they take a temporal dependency on us, okay, because they don't own the information. So they cannot take the decision locally because there are a lot of other systems. So they take a dependency on our systems. And when we have a problem, they just cannot sell, which is a very bad decision for a selling platform, okay? Well, yeah, I mean, when you have a system that say, oh, no, sorry, we can't sell you because this downstream system is not working, it's not a good strategy. Sell it and you see after the fact if there is a problem, you will try to fix it. It's a far better strategy, okay? So the thing is that to cope even with this there is a large amount of data. I mean, I send 1 terabyte of data every 3 days to external systems, which is, yeah, a decent amount of data. So we have to send all this so that they can do all their business without us after that point, okay? The usual way to most people who are not understanding correctly the problem of selling hotels could say, yeah, a better thing would be to have a single system that has all the information and everybody will go to this system to get it. But that is not resilient and it will be slower because you have the speed, the delay that are aggregating all along the way. So, yeah.
Could we get the mic again? Sorry. Thank you. That's such a good question.
Sorry. So, for instance, I have a room in New York I want to sell, and somebody in China is looking at it, and somebody in India or in Europe, wherever.
Yeah.
So, and they press the button at the same time. Do you have the location of the data, the aggregate that actually represents the room that you can book? I mean, let's forget overbooking. So let's say we can't do it.
Yeah.
Do you have the aggregate in one place, like say in New York, and the signal has to get there, or is it replicated and then you have to do a resolution?
No, it's actually what is happening here. So the thing is that mostly it's not a problem, because if you have 10 rooms, 2 bookings arrive, each people are not taking this room and the same room. They just take 2 rooms. And if you have 10, it's not a problem, okay? The only problem is with the last room, because you can oversell it, of course. So no, the system just decide to book the room there, and the other system decide to book the room there, and then we get the information and we see what's happening after the fact. Mostly, overbooking is even not a problem. You know why? Because cancellation.
Yeah.
So, yeah, you sold, at some point you sold 11 rooms instead of, but you have only 10. But if anybody cancels before that night, your hotel is full and it's better for you, okay? Yeah. If you refuse the sale, you will have to find someone after the cancellation, and you already had someone, so yeah, it would be too late. You will have to find someone else. And this is where domain-driven design on all that is really important, because you, as a developer, it's really hard to take this kind of decision alone. You have to talk about business. It's a totally business decision. It's not technical at all. But the thing is that primary thing in this business is doing business, not looking database rows, you know. And yeah, you've seen on big web selling platforms on the web that usually when they don't have the item you want, they just say, okay, we will get some new one and send it to you. They don't say, we don't have left, and sorry. Okay, so when there is an overbooking and nobody is canceling, the strategy is just find another room in a nearby hotel and move the people with a bottle of champagne, and people are usually happy, so it's okay. Business. Yeah, business first.
This would be a great thing to go into more detail as well over drinks,
yeah.
I think, afterwards. Has anybody else got any other questions? Got one over here.
Thank you for talk. I have a question which is kind of related to the previous question.
Yeah.
So the aggregate is a kind of boundary, right? And what is inside is consistent, and what is outside is kind of eventually consistent.
Yeah, exactly.
My question is, what would be your recommendation when you choose what to put inside and what to leave outside? Or if I rephrase, when to change the boundary of aggregate?
Yeah. The thing is that most people get a bit freaked out by the fact that as soon as we say that, it's a bit like, oh, so we need to implement eventual consistency on all that. This is not what I'm saying, okay? So it's not because you don't have to that you have to not do it, okay? So we said inside it has to be consistent, outside it doesn't have to, but you don't have to be inconsistent by default. You can, if you want to make a big transaction with 10 aggregates, you can still do it. If your aggregate is right, you don't need it. Okay? You don't need it. So if you want, you need to split it in smaller batch or process it individually, you should be able to do that still. Okay? But if it's easier for accidental complexity to do everything in one transaction, it's okay since it's not required, but it's not required to not do one transaction, okay? So people relax. It's okay to have several aggregates in the same transaction. But for the boundary, the thing is that I really encourage you to learn about event storming, because event storming is defining aggregates as being the minimum amount of information you need to take a decision. You look at the events of things happening in your system, and if they need to share some knowledge. So if something happened here and it's important to take another decision after that, is that you need this information, so they are related. And this is usually where you have your aggregate. So it's a very good way to get small aggregates. And often aggregates contains far less data than what we think it could. So, because you actually just the minimum data you need to take a decision, which is usually not that much.
Okay. I think if we have any more questions, if we can take those, Jeremie, in the after party. Thank you very much once again to Jeremie, everyone. Thank you.